Biostat Squid. In this video we will go through a step-by-step tutorial to visualize your pathway enrichment analysis results. We will explore different ways of plotting our gene sets and their genes after performing functional enrichment analysis with clusterProfiler. This is a continuation of my first video on performing pathway enrichment analysis with clusterProfiler, so if you haven't yet, check it out. And if you perform pathway enrichment analysis with a different tool or package, don't worry, this tutorial will still be useful. Just make sure your starting data frame has all the columns we need for our plots. So for this tutorial you will need R or Rstudio. You will need to install the following packages. And just a reminder that all the code you see here is published in my blog post too. The link is in the description down below, so if you'd like to copy paste code, that's an easy way to do it. And I think that's it. So if you're ready, let's dive in. Great. So if you followed my previous video on pathway enrichment analysis, you already loaded all the necessary libraries and so on, but we will just quickly go through it. So I like to clear my environment before I start, free up memory, set a couple of options. Then I'm going to load up the libraries we need. These are a couple more than the ones we actually need, because they were part of the first part of this analysis, but it's important to have enrichplot, which is the library we will use for visualizations, and ggupset. Other than that, I will just set some relevant paths where I will output my plots, but this is not necessary. Instead of storing them as variables, you can just hard code the pathway onto the function to actually output a plot. Okay. So we will skip all this since we saw this, this was part of the analysis, and we will directly read our pathway enrichment analysis results. So if you used a different tool to clusterProfiler, I will just show you the columns you should have. Not all of them are necessary for plotting, of course, but just have a look and see if they're present in your own results. So we have the pathway ID, a description. In this case, the two columns are the same. Then we have our gene ratio and background gene ratio. I will go back to them in just a sec. Then we have our p-values and p-adjusted values that show if the pathway was found to be significantly enriched or not. Q-values, another measure of significance. Then we have the gene IDs and the count, so the genes that were found to be associated to that pathway. And then we have the count, of course. Then I just added this column with minus log 10 p-adjusted, so you can easily obtain it from this other column here. And I added a different column, differential expression, which shows which has values down or up, since I merged the results for pathway enrichment analysis conducted on downregulated genes and pathway enrichment analysis conducted on upregulated genes. Okay. So just before we start, I will just go through the gene ratio and background gene ratio with you. So the background gene ratio basically shows the size of the gene set. So for example, there are 94 genes in total that are associated to this pathway, reactome eukaryotic translation elongation, in relation to the amount of genes in our background gene set. So there are 10,441 genes in our background gene set, reactome genes, or genes from reactome pathways, and 94 of them were associated to this pathway. Just a quick reminder that if you followed the previous video, we already subsetted all the genes in our background gene set to the genes that could actually be measured in our experiment. So the genes we actually had in our differential gene expression analysis results. If this is unclear, just make sure you check out the other video or my blog post where I explain it with a bit more detail. Okay, so the gene ratio just shows the amount of genes related to this pathway that are found in our differentially expressed genes, in this case downregulated genes, and this is the total size of our list of interest, so our list of downregulated genes. So out of 805 downregulated genes, 59 were associated to the reactome eukaryotic translation elongation. So hopefully that made sense. Otherwise, leave me a comment down below and I will do my best to explain it in a different way. Okay, so we'll just read in our background gene set. Okay, so for this analysis, we will select only upregulated genes in severe patients versus healthy patients. So with this tidyverse pipeline, I'm filtering upregulated genes, and then I am selecting all columns except the minus log 10p adjusted and the differentially expressed columns that I added in my previous analysis. So I'll just run this, and important, I will assign the ID of the pathway to the row names. So I will just show you what we have now. So our results data frame should be something like that. So the row names are actually the pathway IDs, and the two columns are now gone. So just a side note, an important side note, the pathways that come up after selecting for up are not necessarily upregulated pathways. We're just selecting pathways that were enriched in our list of upregulated genes. And this is a very important difference. So it could be that in our list of upregulated genes, there are a lot of genes that maybe code for repressors or inhibitors of that pathway, in which case the pathway would probably be downregulated in severe patients compared to healthy patients. So that's important. So we are just conducting, or we're just visualizing enriched pathways, not necessarily upregulated pathways, but pathways that are enriched for upregulated genes in severe patients versus healthy. Okay, so these are the column names we have. And for our for visualization purposes, we'll just shorten the pathway names. So we will use this GSUB waterfall, where I'm just taking names and substituting them for other names. So the reason I have all of this is because I apply string to sentence to try and reduce the capital letters to lowercase letters. There are many more ways of doing it, probably much more elegant, but this is kind of a simple way of editing your pathway names. And again, this is totally unnecessary for the visualization, but it'll just make the names of the pathways a bit more readable, perhaps. So now, as you see, the description has most pathways in lowercase letters and just a tiny bit nicer. Of course, there's still a couple of typos I would need to fix, but anyway, you can edit this and, you know, tailor it to your results. Okay, so for our plots, we will use the package enrichplot. And for this, we need to transform our results to an enrich result object. So the way we do that is with this function, new, and we just have to specify that we want an enrich result object, set readable to false. We will give it our results data frame to transform into an enrich result object. I just set a couple of settings over here, arguments, but you might want to tailor them to your results. So for example, I have a human data set, you might have a different species. Then important, genes are all the unique genes that were found in our data frame, so in the original data frame. So I'm just going to go back up and load that result. So these are all our differentially expressed genes. So over here, data frame. So these were our results from our differential gene expression analysis results. So this includes upregulated genes, downregulated genes, and genes that were not differentially expressed between both conditions. So I'm just going to give it all the genes in this data frame. Right, so let's go back to the enrich result object. Then we have our universe, which is our background gene set. So similar to that, I will go to my background genes and give it the gene column. So all the genes that are, all the unique genes that are present in our background gene set. Perfect. And then the gene sets are just the background genes, which associates each gene to a pathway. Great. So let's just run this. And if we now run class of this enrich result object, it should give you something like this, enrich result. Perfect. So now that we have our enrich result object, we can actually start plotting. Okay, so let's start with a bar plot. So a bar plot is a great way of visualizing our enrich result pathways. It basically shows the enrichment score. I'm just going to run this. So you can obviously fix this by reducing the font size or increasing the height of the image when you export the plot. But anyway, it basically will show the enrichment scores, for example, p-adjusted values, and the gene count or ratio as bar height and color. So color is associated to my enrichment score, so my p-adjusted values, which show how significant this pathway was found to be enriched, and the gene count shows how many genes belonging to this pathway were found to be enriched in my dataset. So, for example, there were almost, well, a bit more than 30 genes associated to HIV infection, and this has a very low p-adjusted score, so they're very differentially expressed. Which kind of makes sense, because if we go back to this data set, it was severe versus healthy patients in COVID. So probably a lot of genes related to viral infection or, fighting virus are related to this pathway. We can also use mutate to show different scores, for example, a Q-score. So we can also use mutate to show a different enrichment score, for example, displaying -log10 p-adjusted values. And since we didn't specify, here only 8 pathways are shown. So feel free to play around. But yeah, you can get really nice bar plots with this function. Great. So a dot plot is our next plot, and it's very similar to a bar plot, except that the number of genes is not shown by the length of the bar, but actually by the dot size. So here we say count, so the smaller circles or dots mean that there are less genes associated to that pathway, whereas bigger dots are more genes associated to that pathway. And p-adjusted values are shown by the color gradient. So this is another nice visualization, and you can add a title. There are many more arguments, so I encourage you to play around and just, customize it to your needs. Okay, so next we'll plot a CNET plot, and the function is CNET plot, as you might have guessed. So what does this look like? Well, it's giving me a warning that there are too many overlaps, obviously, because we have too many genes. So of course you can just set the maximum number of the allowed overlaps to a higher threshold. You can find different solutions to it, but it will basically show our pathways in yellow by this yellow nodes and the genes by the gray dots. So basically, a CNET plot shows the linkages between genes and pathways as a network. So obviously the names of the pathways are a bit too long for this to be pretty, so you might want to shorten them if you're plotting them, but anyway, each node is a pathway, and then they have lines coming out that point to all the genes associated to that pathway. So this way we can easily identify clusters of genes that may share common biological functions or participate in the same molecular pathways. For example, in this lower cluster, we see that STAT1, STAT3, and JAK2 are upregulated genes in severe patients with a severe reaction to COVID that are both shared by IL-12, interleukin-12 family signaling pathway and the signaling by CS3, GCSF. Okay, so a heat plot is very similar to a CNET plot. In this case, the x-axis shows the list of genes we have. So these are all the genes. In this case, our upregulated genes, and in the x-axis, we have our pathways. So in this case, we only have 5 pathways. You can adjust thresholds again to show more pathways. But basically, the bars show which genes participate or are associated to which pathways. So it is useful when there's a large number of significant pathways, which makes it easier to visualize. For example, this first gene, ATP5F1A, participates in both the formation of ATP by chemoosmotic coupling and the respiratory electron transport ATP synthesis and the citric acid cycle. Right, so this is another nice way. Of course, you can add colors. Yeah, the world's your oyster, basically, when it comes to plotting. Great. So next we'll plot a tree plot. So a tree plot performs hierarchical clustering of enriched pathways. So many enrichment analysis use hierarchical ontologies to organize functional terms or gene sets, so basically pathways, into a hierarchical structure. So for example, gene ontology consists on 3 main branches: biological process, cellular component, and molecular function. And each branch contains more specific terms organized in a hierarchical manner. So a tree plot from the enrichplot package takes the enrichment results and the hierarchical ontology as inputs, and it creates a tree-like plot where each pathway is represented by a node, and the parent and child relationships between terms are shown by connecting lines. I'll just show you. Perhaps it will be easier to see. So first we need to run this function, which actually calculates the pairwise similarities. And now we will run our tree plot function. There you go. Perfect. So this is what I meant. You see, there's some kind of hierarchical clustering. So for example, it might not be very good. I'm just seeing over here. So perhaps what would make more sense is to have interferon signaling, and then as part of each of the nodes, interferon gamma and interferon alpha beta. But you can have a look to see if it makes sense with your results. So basically here the color of the nodes again represents the significance of the enrichment, and the node size represents the number of genes associated with each term. So this allows us to quickly visualize important or highly enriched terms. And since it clusters them together, it might be good to identify important groups of pathways. So this is also a nice way to visualize our results. Okay, so next we will move on to our enrichment map. EMAP. So let me just show you what this looks like. So as you can see, similar to the CNET plot, we have our pathways organized into nodes, but this time we're not showing the genes related or associated to that pathway. So this enrichment map, it basically organized the enriched pathways into a network with edges connecting overlapping gene sets or pathways. So basically mutually overlapping gene sets, so pathways that have overlapping genes associated to them, they tend to cluster together. And this makes it easy to identify functional modules. So for example, here we identified a functional module related to interleukin signaling. Here we have another functional module related to ATP production and the respiratory electron transport. Here we have another one related to interference. And as we, just like in the tree plot, the node color represents the significance of the enrichment, and the node size, the number of genes associated with each term. So bigger nodes mean more genes associated to that term. Obviously, nodes that are more general, for example, signaling by interleukins, are more likely to have a larger number of genes associated to them than nodes that are more specific, for example, interleukin 27 signaling. So I think that's all for the enrichment map. And finally, we will get to our upset plot. So here I have another G-sub function, which will basically reduce the amount of words in this long pathway. So I'm just substituting it for visualization purposes, totally unnecessary if you want the full name. But I will just show you how it looks like, the upset plot. Nice. So I'll just zoom in. So this is why I reduced the amount of words in this pathway name, because it was very big. But otherwise you can just keep full names and maybe reduce the font size. Okay, so an upset plot is an alternative to a CNET plot, and it emphasizes the genes overlapping amongst different gene sets. Basically, we have our pathways here. Here I'm just showing the first 10 pathways, I think. Here we have a bar plot that shows the amount of genes associated to that pathway. For example, there are 25-ish genes associated to signaling by interleukins, and these dots and bars just mean where are these genes present in which pathways they're present in, so that it just highlights overlapping genes. So for example, we have almost 15 genes that are related to interferon signaling and interferon gamma signaling, for example. Over here we have a very small number of genes, so around, I think it's only 2 genes actually, but they're associated to a large number of pathways. So this is also quite a nice way to visualize our pathway enrichment analysis results. And depending on what you want to show, you might want to subset the pathways to just show certain pathways you want to highlight, for example. And of course, in all these plots, you can customize colors and the font and, you know, typical plot visualization settings. Okay, so as you saw, I assigned all of these plots to P1, P2, P3, P4, P5, and so on. I will just do that now, and I'm creating a plot list, so a list of plots basically, and this is if I want to save a lot of plots all at once. This is a little trick I use, it might come handy. So I'm just setting the name of my path, my output path, where I want this to be saved, and then for each plot in my plot list, I basically open a PNG file, and then I print the plot. So this is within a loop. So first I will be equal to 1. So the first plot in the list, then the second, then the third, and so on. So for each of them, I'm saving a PNG image. So this might be a little trick you can use if you want to save a lot of plots all at once. You might want to group them. Actually, there are many libraries out there. For example, ggArrange or Cowplot are great libraries that can be used to arrange a lot of plots into one if you just want to export a single PDF, for example. Nice. So these are some of the ways you can visualize your pathway enrichment analysis results. If I've missed any or if you'd like to see more, let me know in the comments down below. Thank you so much for watching. If you're new here, don't forget to subscribe. Let me know what you thought of this tutorial. I really hope it was helpful, and I really appreciate all your comments and support. Have a squid-tastic day and see you in the next one.